All right, we're very happy today. We have almost PhD, almost Dr. Yudai Tanaka.
Yeah,
I would just let him take over.
yeah.
Yes, this is not our introduction.
Try to hide this. Okay.
Yeah, you can try.
Can you hit okay? All right.
You can hit the okay. All right, so you need to find your mouse.
Cannot find that. Static HCI program.
Yeah. Is it to the left or to the right?
Down.
Yeah.
All right.
Okay.
All right. Okay, so I can just take over. Very glad to see everyone. Very glad that I gave the talk in a very interdisciplinary, interactive open environment. I really love atlas at sea water and integrated physiology. I'm Yudai Tanaka. I'm a PhD candidate at the University of Chicago. I'm coming from the background of video science, embedded systems, and I'm a builder. So I build systems. And what I built is like wearable assistive devices that assist, empower, augment users' abilities by leveraging our physiological and perceptual principles. And the question that animates me while I'm building these software and hardware systems is that how can computers could go beyond the screen and directly empower users' abilities in the more physical and skill-based tasks? Obviously, today's computers and laptop, you can do a lot of things by searching, creating a RAM, watching videos to have an instant access to lots of information. But my claim is that these informations are pretty much restricted behind the screen. And when you really actually want to learn something about more physical and skill-based activities, for instance, using this tool, you can, of course, like create an LLM on how to use this tool, saying the LLM will say, give you a step-by-step procedure, and then you can get some procedural knowledge. Or you can watch a video of someone actually using it to see what might be the posture or timing of like the strokes and so forth. But the critical thing that media doesn't communicate in this situation is that how much force should I put in? Since the very, very critical information that the users should know in this specific task. The list goes on that if you want to learn like how to play instruments, you can watch the videos of someone playing, but you never get the tactile dexterity they are feeling, which is pretty critical here as well. Other thing would be body coordination of like a professional skilled player in athletic activities. You also cannot feel these tacit information, the embodied information in your body. You can't feel that from the laptop. So what I just described goes down to this one line, that all the way goes back to the Norman's principle of like reading and seeing, understanding is not really the same as feeling and doing it. What I'm saying here is today's interfaces are very rich in audiovisual and language-driven media, but they don't really extend to inform these kind of properties of information such as tactile, kinesthetic, and coordination of the body. So I want to enable interfaces to present these embodied information. And if we can do that, then it would empower users' activities and abilities beyond the screen. So this is the vision I have. And I have built hardware and software end-to-end systems to that end. But I also acknowledge that this is not the problem that only one person is tackling. In fact, this has been like fundamental challenge in the field of human-computer interaction for more than 50 or 60 years. But in terms of like the way we interact with computers today, we haven't got there yet to really like appreciate these informations directly communicated by computer interfaces. So I'm wondering, what is essentially the bottleneck? So I really want to walk through what might be the fundamental challenge here with all of you together first. So I'm giving you a little bit of background here. I believe bottleneck here is fundamentally how computer interfaces communicate present information to our sensory modalities. When we think about the way interfaces output information, it hasn't been changed as Jeter was documented in 2014 that from the desktop to mobile to wearable spatial displays, computers always follow the same principle in accessing our audiovisual senses, which I want to just step by step go through with you in this example of a person having an augmented reality interaction. They're seeing her colleagues, and then they're hearing her colleagues' voices, essentially like Zoom chat, while doing some physical activity in situated scenarios. And she's pretty much receiving audio-visual feedback that she can see the colleague because the computer generates the light and directs it to the eyes. And similarly, she can hear her colleague's voice because it generates the sound wave and directs it to the ears, right? For audio visuals, as you just saw, it works pretty well. So let's apply this approach of stimulating the endpoint of our nervous system, namely, you saw like eyes and ears are the endpoints of our nervous system for hearing and seeing, right? So let's apply the same principle to also communicate the non-audiovisual senses such as touch and movement. For instance, this colleague tries to communicate how he would like manipulate the tool that she's grabbing. Is it possible for computers to directly output such information to the user here by following this endpoint approach? Applying this approach, what the computers would do is it generates vibrational force and directs it directly to the user's skin. Well, the skin is the endpoint of our nervous system for sensing the somatosensory and for kinesthetic information. Devices look like this, as you see on the right side. It would cover up the user's entire skin, so it doesn't seem to work because that the user should feel the natural dexterity and the feeling of using the tools in this real world activity on the real time. So as you can see here, we can't just resort to these devices here. And the distinction I want to just highlight here is from this 1 minute of discussion is eyes and ears are non-contact senses. So it's easy to resort this endpoint approach to let the interaction happen. But skin or body, unfortunately, are sense that requires a direct contact to perceive. This is fundamentally the restriction that encumber the computer interfaces to output the information directly to our bodily senses. So naturally, I'm wondering, how can we bypass the contact, right? To bypass the contact, I look beyond what's going to happen in our perception system, like after skin. So obviously, when a vibrational force or stimuli applied in our skin, mechanoreceptors convert these stimulus into electrical spike trains called action potentials. And these spikes are traversing through the nervous system, and eventually it leads to the somatosensory cortex. That is essentially the unit of perception that the user will feel as something is touching the finger, right? So when you think about that, vibrational force doesn't directly create perception. It's these electrical spike chains that creates the perception. So if that's the case, I would naturally wonder, can we directly apply those spikes into the nervous system that the neurons would respond to by skipping these convergence step from vibration to the electrical signals? And if because the spikes are directly creating the perception, it would result in a similar feeling that the user would feel in the skin region that's not directly encumbered by the device. So this is my approach that I directly injecting the signals into the nerves to bypass the contact, to tackle this bottleneck of interactive systems to output embodied information to our senses. So my past 6 years of PhD research is broadly around these areas, especially on these topics of installing abilities into users' nervous system. Today, I specifically want to focus on these 3 papers that represents very important elements of this notion of installing abilities. One is how can we align these interfaces to the user's physiological system, and how can we also build a computational adaptation that builds designed for the user's psychological constructs, and what might be the path to build the general purpose interfaces of this kind. Along with talking over this, I just want to highlight the contribution, the nature of my work's contribution. My contribution is technical and systems contribution. I build systems that orchestrate the physiological and perceptual complexity in our body to demonstrate the technical feasibility that it is possible to build the end-to-end interactive system that could move toward installing the abilities into our bodies. So let's get started. So I start with an example. So here, a user is doing DJing. So essentially, the computers have all this information that what is the best way to place the hands on the turntable and when they should release and so forth. These informations are directly communicated to the user's body in my system. Normally, the user has to look at their laptop and the side by side to see to do this kind of tasks. But I'm directly try to stream these kind of bodily information to the user's nervous system that they can feel in their finger palm. Another example here, the user is changing the speed of the truck, and then the system can directly tell them that what speed is the most appropriate, so it's matched to the other truck that they should mix to. The most important thing I want to highlight in this example here is the user is wearing this device. When you look closely into that, the user doesn't wear anything on the front side of the hand. So everything, cables and electrodes and everything is on the back of the hand. But we are creating the perceptual illusion that they actually feel the sensations directly coming from the finger pads and the palm, in total of 11 different locations from the front side of the hand. How is it possible? We have electrodes on the back of the hand, and this is a cross section of the radial nerves and median nerve. Electrical currents applied at the back of the hand is non-selective, so it's actually stimulating both sides of the nervous system. But here's the interesting part. We evolved from across the history of the human evolution, and we've always using the front side of the hand, from hunting to collecting items from the ground and so forth. That resulted in this very asymmetric distributions of the mechanoreceptors on the back of the hand and the front side of the hand, more than 60 times. So obviously, the front side has much higher tactile sensitivity in any kind of stimulus that is applied to the nervous system, including the electrical stimulation. This means that if we apply the weaker electrical currents, and then gradually increase the intensity one by one, the first side that starts feeling any vibrational feeling is actually the front side of the hand because of this asymmetric sensitivity. So this is essentially the principle that we discovered in this project to enable this interactive system that can create the selective tactile feedback from the back of your hand. This resulted in our four-hand interfaces that can selectively control the sensations in front of the hand from the back of the hand. Let's talk a little bit about the hardware side of this. So the hardware inside it looks like this, communicates with the laptop through Bluetooth, and then receives any information that they should output based on their clients. And inside of the hardware, this is the schematics. First, to generate the electrical stimulation that we can reliably output to the human system, we of course have a current control stimulation source, which means that regardless of how conductive your skin is, the output of the current level is always constant. This is very important for safety. From there, we are using a 6-channel analog multiplexer that is really fast in switching, less than a microsecond. This allows us to build this 11 independent programmable touch feedback in the front side of the hand that is more than 1000 Hertz, that is matched up with our perception of our touch in the hand. We of course evaluated this system with a human subject study. Essentially, where does the feeling occurs? 12 participants, perceptual localization tasks in total, more than 360 trials. We built at the end of the day this kind of heat map about where they felt. Aggregating all this data across 12 participants, happy to say that more than 90% of the sensations are actually coming from the front side, not the back. Spatial distinction across these 11 points are quite robust as well. So we can say, yes, this can create more 11 points of independent touch feedback. One other example I just particularly want to highlight is imagine a person is making something like a sculpting task or a modeling, physical modeling task. Our nature of not encumbering the front side of hand allows, of course, the user to directly interact with the physical object with their palm side of the hand, but we can also overlay whatever the reference information the computer should have on top of that they feel in the reality. So this is kind of like CAD, like computer-aided design, but that's directly embodied in the user's body. I think some of the nature of these works is like, yeah, it's kind of funny, like, it's a good demo, but how does that actually scale to, practical interfaces? So of course I did that. So with collaboration with research, as a research intern at the Meta Reality Labs, we built essentially this kind of like a wristband that in the vision of integrating this kind of like feedback technology into like Meta's EMG wristband technology. So it can sense that the user's gestures that they already have, but on top they can feel the touch, like confirmation type of like touch feedback in their finger from the wristband. Dunning and doffing is extremely easy because we built the conductive elastomer electrodes. It's working with a material scientist that all the electrodes are dry. So it's not like medical grade electrodes, so that is sticky and adhesive. This is like essentially pieces of silicone, so it's essentially very easy to taking off and on. It's essentially any wristband that exists, like you wear on every day. We went even further and how much we can do in even like controlling the user's finger motions based on the functional muscle stimulation technology integrated into the user's smartwatch. This is actually the consumer Samsung Galaxy Watch that we kind of like miniaturize everything to incorporate control unit, channel multiplexing, and power supply, everything into the watch band. And you can see this backside of the watch is electrodes to directly apply the electric stimulation. Coming back to the vision, I want to empower users' learning and skill acquisition abilities of like playing instruments and making stuff or learning new skills. Imagine your smartwatch can teach you how to play the drum. That's kind of the vision I have. Of course, by now you might be wondering that these things are taking over your body. So ethics of these intervention technologies is ever really relevant. That's why I've been organizing the symposiums on responsible research on this kind of neurotech collaboration with these various institutions. We organized symposium in Kai 24, and so there's an upcoming one in Kai 26 in 1 month. I've been also collaborating with UL, which is a safety organization. You might find the logo in the back of your laptop to run a psychophysics study to inform the safety level of the leakage currents or electrical currents that is applied to the human body. So with that, I've been working on this research norm and risk mitigation, safety. But when we think about the ethics, key challenges is always happening during every single interaction. That is, when you are using these systems, these are physical feedback, that overrides your sense of touch, that might override your body movement. So if you have your own intention and you're doing the task on the real time, at the same time as the systems help you, there might be some conflict that users that is against the user's own intention action, right? So this is actually well documented in prior works that say conflict between the system and the body's internal voluntary signals. Or like some of the participants from these kind of studies said, I felt like my body was hacked. And I believe this is a very, very huge problem, right? We need to address. And this is also very important in a sense. Obviously, this connects to the loss of sense of agency, right? So if you don't believe that you are the one who is doing the task, you are disengaged. You lose the motivation. That's very detrimental in any further applications in the domain of learning or even rehabilitation. So I'm really eager to build a system that can align to these users' intentions, these psychological constructs on the real time. For instance, for this time, for agency. So this is my upcoming work. It's going to be published at Kai 26, that I built a system that essentially make you react faster. So this one is a fail case. So user has our system off right now. So they have this very fast moving ping pong ball that normally it's hard to catch, but we can augment their user's reaction time effectively by 25 milliseconds that the user could hit that ball. I'll later cover the user study that I actually validated, but important thing here is that we built the system such that it is always aligned with the user's intention of movement. So in this case, this system doesn't trigger when the user doesn't want to move. Only triggers when the user wants to actually react and do the task. So assistance is always aligned with the intention that it preserves the sense of agency. The trick here is we are Closing the loop with electromyography, EMG, detects the user's onset of the early onset of the action potentials in the muscles. And only after detecting that, we triggers the muscle stimulation. And that way, the system always know the answer, whether the user wants to move or not. But you might be wondering, if we already know the answer, is it too late to activate the stimulation to actually make you move faster? So let me actually go deep into what's happening behind the scene. So what we are doing here is like essentially building on the Henneman size principle. When you are moving your body by yourself, you are essentially coordinating different sizes of motor neurons that to kind of control the force precisely. But external electrical stimulation can actually more aggressively recruit the motor units in a sense that it's faster in start contracting the muscles. This is the plots from our technical evaluation that gives us like a 25 milliseconds of time window that the stimulation driven movement is faster than you can voluntarily move your body. But we only have 25 milliseconds. So any kind of latency from the system is very critical. So I built the closed loop physiological sensing, like a muscle sensing and a muscle stimulation system that completely operates on the edge to mitigate the latency. So let's walk through that. We have electromyography sensor that has some outputs the envelopes of the amplitude of action potential. It comes with 120 microseconds. This is very conventional setup of instrumentation amplifier and notch filter and analog filtering to reduce the noise. And then we have this on-device signal processing that happens entirely within the microcontroller. We are just essentially doing adaptive Schmidt trigger that comes the majority of the latency, which is 170 microseconds. Once the system makes a decision to activate the stimulation, the actual switching on the hardware is extremely fast because we are resorting to the optocouplers that is very fast in switching. So actual switching takes less than 1 microsecond, resulting in like and also I want to make a note on like noise reduction because both electromyography and the stimulation happens on the electrical currents on the device. So stimulation would accumulate as a noise for the muscle sensors reading. So we have RC breather networks mitigating the sensor noise. Overall, this results in like 290 microseconds, not the milliseconds. So it's less than 0.3 milliseconds. So we can leverage the most of the time window we have, 25 milliseconds. It's just the summary of that, which we evaluated in our user study, human subject user study, again, 12 participants, 1,080 trials in total. We validated that compared to no assistance, users' reaction time is faster by about 25 milliseconds. We also, of course, also evaluated the accuracy of like classifying their intention, like triggering or not. This is a simple binary classification. We got the F1 score of 0.95. Most important part of this study is like, does this actually preserve the user's sense of agency? So what we did in this user study is not just user see a light and then pressing a button, which is called the simple reaction time test. We have a little bit one level complex version of that, which is when you see a green light, you press a button. When you see a red light, you shouldn't press a button. So user makes a decision, and then our system adapts to the user's decision and intention. So we have essentially go case, which is a green light case, and no-go case, like a blue light case. So baseline here is an open loop EMS that muscle stimulation that always triggers to regardless of the user's intention. So the system doesn't have any notion of aligning with the user's intention versus our approach of systems like on the edge adapts to the user's intention. And this is explicit agency score report, 1 being you didn't do the action, 7 being it was my action. So when we plot these results, it's very clear that the difference between the sense of agency that user reported in our adaptive system versus the baseline. Especially the gap is bigger when the system adapts not to override the user's intention, because that's really annoying when the system overrides. When you don't want to move, the system overrides to move, right? A little bit step back about a little bit of conceptual note in here, that what I want to do here is we want to make a system that could improve your performance, augment your ability, assisting. There's this classic trade-off between this performance improvement and the sense of agency. Any of these rehabilitation or human augmentation systems from literatures across HCI and beyond, there's this steep trade-off, right? As the improvements from the system and assistance gets bigger and bigger, the less and less the user feel that they are doing the task, right? What I want to do here conceptually, this is a conceptual diagram, is that can we nudge this trade-off curve slightly to the right, where we can create this illusion that the user feels that they are doing it, but they're becoming better significantly. This is a really important, I believe, important design space to balance users' agency and performance, which would translate, I hope, to rehabilitation with agency. What happens if we can build a system that facilitates users gaining rehabilitation, that the system could make the user believe that they are contributing to the rehabilitation? Does that improve their rehabilitation outcome or not? I think that's a really interesting research question. That being said, you saw two of my projects here. Both of them are about hands and arm motions, but we are talking about embodied abilities that's across the whole body. How can we build potentially in the time frame of decades or 100 years? How can we build the general purpose computing interfaces that augment or support every type of different bodily abilities? And that's the vision I have. And I did do work that could potentially be a path for this kind of general purpose interfaces, which I want to discuss. So nerves are actually converge at the brain at the end of the day. And when action potential, when you think about the touch, when action potential reaches to the somatosensory cortex, that's when you feel that you are touching something or something hitting you. So if that's the case, then how can we actually directly inject the signals to the brain? So we don't even need a device that's worn on the arm or feet. So this is the work I'm showing right now. We call it the haptic source effector, and you will know why. So this person is whole body virtual reality training, and this person wears like a helmet device that incorporates virtual reality headset and our custom robotic platform that houses transcranial magnetic stimulation, like non-invasive electromagnetic brain stimulation technique. The reason why we are resorting to magnetic stimulation here is that the brain is concealed with the cranial bones. So we can't just directly attach the electrodes and then it doesn't create the sensations. So we needed this methodological shift to electromagnetic stimulation. And what's happening in this right moment is that our robotic platform, the computer system, knows where should be the primary motor force region that corresponds to the hand sensation, and then the user should feel this recoil in their hand. So the robot locates the coil right atop the right place on the user's brain. We have some calibration protocol prior to the actual experience, and then they activate this electromagnetic pulse that innervates the lesion, and from the brain they feel this force feedback, and they're wearing nothing on the hand. Thankfully, the robotic actuator now relocates the non-invasive brain stimulator to the lesion that corresponds to the foot sensation on the left, and then they feel in the foot.
Let's get this one.
And despite on the body, I mean, this is kind of like proof of concept demo. But what I want to make as a claim here is like a conceptual contrast between any existing most of the haptic devices that is designed for a single purpose, right? If you want to feel something in your foot, you should wear the device on the foot and so forth, arm and shoulder. Here we have a centralized wearable device that sits on the user's head and then has a feedback on the user's brain. And in that way, we have a centralized and kind of like a generalized across the different parts of the user's body. If I say generalizing across the user's different parts, then you might be wondering, how do you know that? So we did a study with human subjects, N equal 12, as again, perceptual localization task over 500 trials. we define a grid on the user's motor cortex area, 9 points, and then we essentially modulated the amplitude of the electromagnetic feedback, and we observed how many different sensations arise from these different locations. These are all aggregated across 12 participants. And this percentage means how much of the trials successfully elicited those feelings. When we visualize in a different manner, we have two types of sensations. Now this is a little bit getting in the way, but it's like movement and touch. And for the movement, we could create the involuntary movement from the brain stimulation in the jaw, forearm, fingers and wrist, lower leg and foot, these 6 locations. And for touch, that doesn't move your body. So it's like a pure tactile sensation in the palm and the foot. So total, 8 different sensations in one side of the body. So it totals up to like 16 different sensations just for the brain. Of course, I'm going to talk about how I made this device. So this is a medical grade transcranial magnetic stimulator that is housed in this custom robotic platform that can move the coil both left and right, and front and back. So it's essentially for folks who are doing computational fabrication, it's essentially repurposed 3D printers. We are using the motors, separate motors, and the passive rating structures, but it's in a different customized form factor. On the control side, we have this like training that's running that's paired with the control of the locations and the intensity of the stimulation. So users, depending on what the user is doing in the simulator space, that the system allocates the amplitude that is appropriate for the feedback that is communicated through open sound control, serial communication to the magnetic stimulator. And for the location of the coil, it's also through the serial communication between the VR client and our robotic platform. The cool thing here is like sometimes, because we are moving the coil along the way, it takes like some time. Like user fields should feel now, but it takes like 1 second for the thing to move to the right location. So that's why we have a bi-directional control. So the system interactively controls the visuals and interaction state of the simulator that the user can feel like the feedback doesn't happen until the system is like ready to output the feedback. That is, in the meantime, the visual side of the virtual reality system outputs some natural like visual effect that makes sense, like charging up the shooting, or the enemy doesn't shoot you until everything is ready. This is also compliant with the safety guideline of transcranial magnetic stimulation, where like nothing should happen until 5 seconds should elapse from the previous stimulation based on the intensity and frequency of the transcranial magnetic stimulation we are using. We did another study to really probe into how user would experience this first of its kind brain haptic interfaces. Everything, by the way, all this human subject study went through a biological science division's IRB protocol. So we are essentially following the same process of getting approval from clinical studies. So here comes the user's reaction. So they just felt in the hand, and also they felt in the foot. There are 2 objectives for this study. One is why we wanted to understand how do they describe the sensations. We have 6 options from tapping to stretching, and like the majority vote would be the combination of the tapping and the vibration, the kind of feeling. And here's the raw quote of participants' qualitative feedback from the semi-structured interview. One interesting note I would make is that they're not wearing anything in the hand, and yet they feel the sensation in the hand. And this, compared to existing haptic feedback devices, it makes more natural, because when you actually touch the chair or desk that you're not wearing anything, that's the most natural way. And when you're wearing some kind of glove-like devices and you feel like you're touching the chair, that's kind of expected. The device should do the job, right? But in our case, we don't make such kind of expectation. So that might be an interesting follow-up direction. I want to make a note about how I would, when I say general purpose, before I started talking about this project, I said general purpose. General purpose is not just about, feeling sensations in your body, right? Our brain has much more like multi-regional brain cortical dynamics. Even for like so this work is just when we think about mapping in the brain, we're just having a system that works with motor cortex. But even for very simple actions like you see a light and you press a button, the dynamics in the brain is pretty complex. You get the visual cortex, primary visual cortex, primary auditory cortex, to parietal cortex, to premotor cortex, to motor cortex, to drive your finger to press a button. So human actions are very involving multi-regional brain dynamics. So I want to talk a little bit about how we could also move into this kind of brain dynamics, that's interactive system that supports these innate dynamics in the brain. So in my latest work, I did a system that similarly make you move faster, like the ping pong one you just saw, but by stimulating the user's motor cortex with a sub-threshold intensity, so that the stimulation itself doesn't make you move. But in that way, we are essentially facilitating this process of like action potentials projecting from premotor cortex to motor cortex to generate the motor command to move your body. So in that way, we can make you move faster because it takes less time for the motor cortex to hit the excitation threshold to actually move your body. So that way, we are not stimulating you to move. So this is essentially user's pure voluntary action, still accelerated. So when we evaluate in the same way as the previous work that I did demonstrating the ping pong reaction time, the agency score, even compared to like wearable devices that overrides your muscle activity, is much. So this approach is much higher than such conventional approaches of stimulation. So that was like a final note for like how we can even moving beyond to brain dynamics. And this is just a first step I did just recently. And now I want to make a note for my future research agenda. So as a researcher, I built the system, and my goal is to empower users' abilities in physical and skill-based abilities. And there's lots of challenges coming forward. How can computers be more context-aware, more predicting in the user's intentions, and so forth? Lots of things are so tough to solve, but recently we are seeing this opportunity horizon of like generative models and AI systems accelerating into the real world. So in the robotics domain, people started solving like in a fascinating way that enabling robots or humanoids to have these embodied perceptions of predictive reasoning of the world. Some people say world model and so forth. So in terms of the computation, I believe there is something that we can leverage or learn from this research. But I think, and even though this trend of physical AI might unlock very interesting new opportunities of AI directly empowering our abilities, which might be very powerful for rehabilitation skill acquisition, I don't think just plug and play approach of like just transferring the robotics model to human devices would work, as documented by Shia et al. In the recent papers of the wearable robotic devices. Because robots and human are very different. We have these psychological and physiological features that the systems need to orchestrate, right? So we really need to bridge this gap. And I believe this is what I've been doing for 6 years. I've been building interactive systems that orchestrate these psychological and physiological restriction. So on the meta note, I don't change research direction. So I think what I've been building is similar in this kind of very broad perspective. I built the system that adapts and aligns with the user's psychological factors and physiological factors to accelerate the deployment of these systems in a domain such as rehabilitation, learning, and clinical translational applications. On the psychological factors side, what I'm interested in is like, let's say, sense of agency. So right now, much of the practice and the prior work builds on the user's explicit report based on the questionnaire. When we think about the real-time system that could directly adapt to the how much ownership that they should have, or engagement or motivation, and so these kind of like cognitive and psychological constructs, we first need to formulate these kind of conceptual and cognitive concepts into like observable physiological and behavioral markers. So we can build the computing approaches that can directly adapt to these as a, for instance, like reward component in reinforcement learning. As an example, definitely like this the second work that the pinpoint one can incorporate more fancier computation models to better adapt to users' intention or agency. But also another work that I'm currently doing with Google is how can we adapt the cognitive assistance when you're lost in, let's say, following the recipe of cooking, and the device should know the right timing, right moment when the user needs assistance. How can we know such like cognitive like demands or like cognitive loading state? So we are like resorting down to physiological sensing technology such as breathing, eye gaze, and so forth to build the model that the system can classify when the system user needs assistance. On a physiological note, I'm interested in solving this very fundamental challenge of this neural brain-computer interface or neural intervention that much of these non-invasive approaches are still pretty imprecise. And let's say, for instance, creating the sensation, like moving a single finger from the stimulation, different current path is required as the user rotates their wrist because internally the muscle location moves. So I'm interested in closing the loop with like sensing, for instance, impedance tomography or electromyography to real time inform the system what the user's physiological state is, like what are the like locations, the bones and muscles and so forth, to improve the precision of this simulation technique. From there, everything is like based on the complex dynamics on the brain level, as you saw in the last few slides. So I'm interested in this multimodal intervention architecture, both resorting to brain level and then the nerve level intervention to really support like the real world tasks or rehabilitation. I'm, for instance, interested in this kind of multimodal architecture to support Parkinson's disease case. It's an interesting case of like the tremor happens on the user's muscles, but the cause of these tremors are from the brain. And typically, the deep brain stimulation is used to suppress these symptoms. But we could approach this kind of program by this multimodal architecture that suppress the tremor on the real time with the muscle level stimulation, and it could have long-term modulation of the neural activity on the brain level intervention. I wanted to make some notes about how this kind of like how I envision this will accelerate the deployment. I already started kind of working in supporting people with a diverse background of ability. For instance, with collaboration with Professor Smith at Columbia, we are using the first work you saw, this one, to support the low vision or blind users' braille reading experience. So not just feeling the braille, just the physical braille, you can feel the additional like existence of the annotations and so forth from our system. And the important thing is that in reading braille, you need your full tactile acuity from your skin. So my work is kind of perfect in supporting this kind of situation because our work doesn't encumber users' skin. Another case, the other case here is I'm collaborating with Professor Boss at University of Chicago's neurology on rehabilitation for memory rehabilitation work. So essentially, this collaboration is much more like kind of based on the hardware. So we built that the robotics platform that enables to attach the transcranial magnetic stimulation coil in fixed to the user's scalp. We built the updated version with these wearable devices, and then he found it very useful in like fixing the coil in the location that's necessary to stimulate the hippocampus that is relevant for memory rehabilitation. At the same time, the user can move around because the system is wearable compared to these conventional ways of using the robotic arm to fix the coil. All right, I'm almost done. Takeaways. You can just read, but by leveraging the neural principle and building the real-time embedded systems, we can grant these like digital feedback into the user's physical abilities and tasks. Secondly, I showed that how these devices can adapt to users' sense of agency, but I believe that this could have kind of more implications of different types of user psychological constructs. And that's very important to deploy these systems for rehabilitation learning. And lastly, I believe there might be a path from the brain stimulation to support the user's variety of abilities and activities and building interactive systems for that interface with the user's brain therapy. Thank you so much.
So time for questions.
Fascinating work. I wanted to ask about the your TMS work because I remain somewhat skeptical about how precise you can be with your dose because you're giving this bolus of current like 100 volts per meter in like 100 microseconds, and you're basically bombing motor cortices and motor cortices. So could you comment on how precise you can actually be to augment what you're proposing to augment?
Yeah. So the coil we're using is a butterfly coil to create the focal point of about 8 millimeters of the electromagnetic field that creates eddy currents inside the user's motor cortex. And we are stimulating the motor cortex. And so that's the focal point size. It's not enough to precisely elicit the sensation in, say, fingerpads. So characterization of essentially the spatial fidelity is also part of this contribution. If you have a real-time control of the robotic platform to move the transcranial magnetic stimulation coil, what might be the resolution of the resulting sensations? And as you saw, like 6 different locations that can like essentially when we just think about the upper end, just distinguish the joint level, like hierarchy, like upper rim, wrist, and the finger. Those are the essentially based on the size of the focal point, 8 millimeters. That's a limitation. So that's the spatial fidelity that we have. And on top of that, we have a error from the robotic control, which we characterize as 8.5 millimeters. So the worst case scenarios that might be off by like 9 millimeters, like when we take the half of the diameters of the focal point and the error, and which essentially is what you saw in this user study result. And I think I'll make a note on this that I am not saying, say, TMS is the only modality as a non-invasive brain stimulation. There are other techniques to interface with brain non-invasively. One thing I'm interested in right now is focused ultrasound stimulation. We recently purchased the stimulator for that. There are pros and cons. It has a smaller focal point, but it's a nation's technique that safety and ethical guidelines and in reliably running a human subject study is a challenge. And I'm really interested in advancing different modalities of brain stimulation techniques to,
Can I follow up on that? Because so when you're putting this on different people's heads, how do you account for the size that they have, the fact that they have different
100%,
sizes? Do you have to like train it first?
We have a calibration phase. So we essentially first go through like very canonical, it's called a hotspot search. So we actually automated the hotspot search with our robotic structure. So it actually defines the 3x3 grids and it search every point to find the point that require the most effectively that TMS can create the involuntary movement in the hand and foot. So these two after finding this hotspot for the hand and foot, we just extrapolate to define that the 9 points. So that's a calibration phase. And we actually working with Professor Boss to incorporate our hardware system paired with fMRI scanning of the patient's brain data. So if we have if you have 3D structure of the scans of our brains spatial prior from the fMRI scan, we can feed that information to our real-time tracking system that might be more accurate and probably accelerate the calibration.
So you can make me hit the ping pong ball faster. Is there a learning effect, or am I forever dependent on wearing the device in order to perform?
Yeah, I also had a kind of similar question about, are there any kind of placebo effects? Like, you're kind of saying that, oh, it's happening, but it's not actually happening, so that they kind of off.
Yeah, I think first of all, so I first answered the placebo effect and the learning effect. So the placebo effect is, I think, taking care in our study design that the user's task is always to get as fast as possible. Sometimes in like psychophysics, people do, and we also did like incentive design. So based on how fast your reaction time is, your compensation, monetary compensation from the study actually. So if you press faster and faster, and you get more money. So subjects are really eager to press faster, even in the non-baseline conditions and so forth. So that was for placebo and for learning effect. So our colleagues, I just acknowledge that's not my work. Our colleagues did this the probe into that notion of learning effect about systems like make you react faster using it for extensively 3 hours, and then they have it. And they have just post-study evaluation of like reaction time without the system. And they also asked the participants to come back. I guess it was 1 week later, across the conditions of assisted and non-assisted. They are not using the electromyography. Their focus was just a simple reaction, so it's not about the intention I just showed. But the interesting thing is like, about 8 milliseconds of improvement still left without the device. I'm not sure if that was 1 week or like what was the time gap between the training or not. But it was a statistically significant gap compared to like non-assistants. Yeah.
So I would be concerned about the opposite effect that your brain recorder electrical muscle system would adapt to being assisted, and then when you run the assistance, your reaction time actually gets slower. People actually look at that.
So you're saying that the people get used to getting assisted.
And there's a physiological adaptation in terms of your neural signaling.
Yeah. I think there are two levels. I think there are 2 levels for this question. So first, for physiological adapt, I think this also touches the agency concept that people know that the system will augment your body, augment your ability. Then people might be more like less cautious or like less attentive to the tasks, because if they're doing good in any way, that there may be attention side of like response might be slower, and so forth. And that's something that I also wanted to kind of like tackle a little bit in the agency work. Another thing for physiological side is that we are essentially building a system that makes your ability programmable, in a sense that it can augment your ability, but it could also impede your ability for the purpose of learning, right? If the system can know what might be the best learning or what might be the best level of difficulty for the task at the time that you're learning. And the vision I have here is like, if the system can interactively or programmably make you, let's say, faster or slower, we could avoid people just over-relying on these systems. And that's a comment I would make for physiological side. And on the cortical plasticity side, I say, some people might say this, like receiving these electrical pulses over and over again, then your brain's like plasticity might be affected. I think that I often discuss with the people working in the prosthetics domain, like Professor Sliman, late Professor Sliman Bensmeyer and so forth. People did that scanning of the brain for amputees before the amputation, right after amputation, 10 years after amputation, 10 years of using the prosthetic devices. The representation of the innervation of cortical somatosensory cortex was intact, like completely, like almost the same, even after 10 years of using the sensory prosthetics. So on the cortical side, this is still a controversial topic in the field of neuroscience and prosthetics, but some people may believe that there's not, in a innovation level, like body mapping and so forth, there's not much cortical facility, which is slightly a good news for us, that we don't have we might say that there might not be huge of an ethics concern about using this kind of augmentation device over time, if it doesn't override your nervous system structure and so forth. Yeah.
So in your motor action device, I was wondering, how did you control the simulation for targeted movement? Because in hand movement, you might have both antagonist and agonist muscle activation.
100%.
And
yeah. So I have to kind of separate the demo and study, right? What we did for study is essentially the control psychophysics study of targeting on one muscle, the flexor. So if you, in a sense that we are not doing like very complex muscle coordinations across extensor and flexor and so forth. So it's just focusing on one muscle. I think that might be suffice to answer your question. Yeah. All right.
So you're talking about kind of developing these systems that protect people's sense of agency, preserve people's sense of agency. And that, of course, makes a lot of sense, I think, in maybe like most contexts, but it made me think about like the opposite situation. Like, are there systems where a user would not want the agency, like where it would be beneficial to have the system intervene against your will, and that would be actually beneficial either from a safety perspective,
100%.
Just be fun and
100%.
like how you can't handle yourself.
So I really like this this question, because that's precisely what I'm thinking. So it depends on the application and context, like what might be the best intervention strategy to prefer. And you said what I was going to say, safety. Systems should whatever measure take to protect the users. Like the sense of agency doesn't matter if you're in a critical situation. Another thing here, my colleague did an interesting study about automating your body movement in a boring tasks. In a sense that you are cooking and engaged in something else, let's say writing an essay at the same time. You're like doing this, and then you're writing an essay. One is cognitive and then the other is motor. And this is like just, in a sense, doesn't require cognitive processing. So they did a study. Does that actually help you engage better in the cognitive task if we automate the motor task? So they're in the multitask situation, and they did a study that they actually found that it's called end-back task. So you memorize like the numbers and so forth, and short-term memories and so forth, while you're like constantly like inputting like left, right, up, down kind of thing. And they saw that like cognitive load, NASA TRX, and also the performance in the cognitive task improved by automating the task. So that's kind of like scenarios where the user doesn't need an agency could be automated as well. Yeah. Professor.
But can you bring your presentation tomorrow when we meet?
Yeah, absolutely.
Some of us would like to talk about the physiology in more detail.
Absolutely, yeah. Hey.
I was just curious, this is super interesting, but there's so many things going on. I'm curious what your specialty is, or your lab specialty. I mean, the ideas, the integration, like picking up the signals.
Yeah. So I think that it might be very simplest to say that I'm a hardware person, an embedded system person. build the system, takes care about this restriction coming from complex human physiological systems such as latency, even like psychological concepts like sense of agency and so forth. My expertise is building this system that works out to deliver the outcome amid these kind of restrictions coming from our physiological systems. Yeah. So my lab would be pretty much electronics, hardware,
So it will be collaborative with other folks who are
100%.
sort of doing this.
100%. I'm also interested in on the on-device machine learning, which we actually tried in the Mayo action paper. That we actually first did like very simple recurrent neural network that's essentially as long time memory. Didn't work out. Even we are running out on device that the latency was too big. But might be good to apply these more like data-driven approach for other purposes. Yeah. Hey.
Yeah, so the title kind of reminds me of the movie called Matrix.
Yes. Yeah, essentially,
So
yeah.
where Neo kind of installed
Kung Fu,
how to control
how to
helicopter.
operate. That's a
Operate
B292
helicopter.
helicopter. Yeah, because I have a reference to that.
Yeah.
Like I know what helicopter.
It's a purely embodied one, but when you kind of try to install how to operate helicopter or even like a drive a car, for example, if you just want to actuate the steering wheel or axle, it's not enough for the self-driving. But you actually gonna need to orchestrate the, like a vision or like, most of the kind of stuff.
Yeah, that's why I'm saying definitely like multimodal interventions from vision, hearing, touch, proprioception, even vestibular are necessary. Also, I think this is important to highlight that when I think about this vision of like sci-fi, Neo knows how to kung fu or how to drive helicopter, is like there are two ways to achieve that, I guess. In the long run, what I interested in is like ultimate like speeding up with the learning for these physical tasks, so that the user permanently install. When I say install, that's why I say word installing. When I say install, when you install application to your laptop, it works all the time, over time, right? But right now, what I'm doing is more of like streaming, right? It only works when the system is active. And so I'm interested in to actually go into install side. So like more of like learning, working with learning scientists, working with rehabilitation practitioners and researchers in understanding and building a system that actually accelerates your learning. On the that's what I want to do. Yeah.
Thank you for the talk. Yeah, maybe this is not a question, but I was thinking about the agency side. Like now, like the user doesn't understand that whether this movement is they understand that it's his intention, but it's because of the system, right? So like for like watching like short videos, or then the system want us to feel that we are intent to do something, but the systems are trying to do something, but trying us to not feel we are intended to do that. Or like advertisement side, like when we buy something, we feel that we are buying something because we want to buy it, but like we cannot like distinguish whether it's because of us or because the company want to do it.
Yeah.
So I feel like it's like a kind of like a security hole. Like the system can kind of move our hand without our intention. So like whether like increasing the agency is going to solve the problem or not is acceptable for
100%. Yeah, I think this guy loops back to Kasun's question about what are we designed for and who we are designed for. I think depends on the context. I don't want like meta streaming some art. I feel that that's my intention for buying something. That's really, I'm against that. I think, so in the symposiums that I was organizing, there's lots of discussions about security of these kind of devices. I think with the surge of this physical AI and it meets these advancements in biomedical devices, I think more and more, I believe that more devices would kind of like enables to assist or take over controls of the body or sensation. And these questions about what is the right design, what is the human system alignment, what is the security measures for that are incredibly important. I'm also, for instance, interested in say, what might be the right encryptions for these systems. Right now, we are just brute forcing for the first project about the Bluetooth. It's incredibly easy to intercept the signals and so forth. But we can encrypt that. What might be the reliable computer architecture to decoding these encrypted wireless protocol on the edge and so forth. And that's also avenue for collaboration as well. Yeah.